thank the organization committee to giving me this chance to talk about a topic that we've been recently working very passionately about, which is on a data-centric view of composable NLP. Before I start, I'd like to introduce my co-authors of this presentation. So Hector Liu is currently a lead engineer, a head of engineer at Python, and much of the content from today's talk was based on his own, hands-on experiences of producing production-level machine learning solutions. And Zhiting is also working, alongside, on many of the topics that we are going to discuss. So I guess nowadays, we hear a lot of good AI results, but still we can see a lot of enthusiasm, on leaderboards and benchmarks, which are mainly focusing on accuracy-related performance. These are important benchmarks and dimensions of improving machine learning models and innovations. But on the other hand, it is not just the full picture of why we do machine learning, because in industry, we face very often a new type of problems, such as safety, efficiency, and so on. And also there is a need for good engineering practice, such as robustness, reliability, reusability, standardization. And these may not go hands in hands with the benchmark and leaderboard-driven AI research. So I will start with a few examples in the applications that we're going to talk about today. So NLP applications, for example, has seen a lot of applications in machine learning technology. And such applications include machine translation, for example, chatbots, information retrieval, speech recognition, and so forth. Right? Very often, our results in machine learning, algorithm, and the model design can directly translate to good performance, but not always, because behind the scene of these cool apps, there is always often a big pipeline of additional tasks, starting from raw data processing to integration with scalable systems and other modalities of data, such as images, to drive the results together. And this actually makes machine learning development very challenging. Let me go down to an even more specific example. So recently, my company has been working on some healthcare-related product applications, and this is a typical scenario in healthcare applications. We are given a huge amount of data of very messy quality and also of very many dimensionality and modality. And these data sometimes are structured in tabular form and sometimes are very unstructured. And also you get the image data, DNA, genomic data, vital data, and so forth. And the goal is to create a solution that is compatible with physician's workflow. And what does it mean by compatible with application with a physician's workflow? For example, here, when we are given a radiological image, such as this X-ray picture of a lung, right? It is not just about tagging the image by labeling out which part is abnormal, which part is normal, and doing this kind of object detection related task and tagging. You actually also need to have the ability to integrate such results, with the patient's own clinical history, and maybe also more knowledge and context of the disease itself. And then what you are expected to deliver is maybe a clinical case report, which the doctor can use, to explain to the patients about the caretaking procedures, or to transfer the patient to another hospital so that the next doctor can take on. So these type of solutions, is very complex. When we build it, it requires the interoperation of many components, starting all the way from cleaning the very messy and the low quality and the large volume of data, including maybe even doing OCR, to get the text out of some scanning documents, and then to correct misspellings and the many nuances in the low quality raw data. And then you are going to move on to many steps of data enrichment, such as extraction visual features, extraction of semantic features, And then this data can be now considered as a machine learning ready. You are going to use fancy algorithms to understand the data and then to carry out subsequent tasks, such as text generation, for the reports. And again, this text generation can be of multiple granularity, all the way starting from maybe sentences and then paragraphs, maybe longer ones. Therefore, you need to use sequential models of different sizes. Not alone, there are system infra-related issues which allow you to scale the results or to deploy the results or to do federated learning type of solutions, right? So this is actually a real complex system that is beyond just the algorithm. But what the user will see is a clean interface with all these elements that I just mentioned hidden behind the scene. And that basically challenge we machine learning researcher in terms of how to produce a solution. One may say that nowadays we have a lot of exciting developments in the so-called all-purpose machine learning models, right? They are single models of gigantic sizes, and the hope can be that you just throw in your data, and this model are so big and so richly trained. Maybe they can be multi-purpose and multitask to different applications, and then as a result, you get the hypothesis and predictions and so on out of it, right? So that's one way of seeing the problem. But and also, in fact, we do see a lot of promising progress, in this direction. We see, a amazing, multiplication of model sizes over the past few years. Now we are already talking about, in fact, before we have a chance to play with the model, like the GPT-3 model of with 175 billion parameters, we already heard big companies developing models 10 times bigger than that, or over 1 trillion parameters, right? So this trend of training bigger and bigger model obviously provides a lot of promise for challenging the limit of machine intelligence. Sometimes they can even give superhuman performances on some tasks. But on the other hand, these type of single gen models face difficulties when we are talking about industrial and production deployments. For example, when you need to explain to your patients about why you conclude a particular disease and why you offer a treatment, you would like the model to be explainable so that the patient and also your colleagues can be convinced and also can understand and can even further dive into the solution and to debate about different outcomes, right? And then from a pure engineering point of view, debugging such model can be very difficult. In fact, it is very hard to even trace any bugs in such big models. Maintenance, upgrades, stability, reusability can all cause difficulties in running single black box models. For example, if sometime in the future there comes a new way of tokenizing the raw data, the text data, should we actually rebuild a whole model, or we can adapt this new tokenization into the existing model? That is actually very unclear. Okay. So what I meant to say is that the AI production right now that many researchers or even the industrial players are adopting, by developing and training gigantic big models, is not necessarily meeting the needs, for real world applications, especially when we talk about the industrial production. For the successful industrial production, such as aviation, you will see actually a very different way of practicing, which focus a lot on modularization, standardization, and so forth, right? So system level failures can be broken down systematically into components and at different level of failures, maybe with the help of a fault tree. You can also simulate the results, to assess the risk and the benefit at low cost. So these are all not quite readily available yet in our current, AI research. So I believe there is a need to move away from crafting bigger models when we are talking about industrial production to a modularization and a standardized way of producing AI solutions. So along the way, of this trend, I would say there are already, a great deal of excellent effort devoting to making toolboxes, for machine learning problems, especially in the NLP space. Here, I want to give a quick overview and a summary about their design principle and their virtue, and maybe also their limitations. Right. For example, we see a lot of recent successful libraries, which we can call model-centric. Okay, the model-centric library, includes built around a collection of highly successful models to make them easily accessible, right? And also there are task-centric libraries that attempts to solve very common, recurrent tasks such as part of speech tagging, name entity recognition, and so forth. And also there are much bigger solution-centric libraries, which could be, providing end-to-end solutions to complex tasks such as conversational assistants. So let's dive each of these libraries a little bit and to see what is their design principle. So for the model-centric approach, they are built on, an ecosystem around a few type of models. For example, we all know that the Hugging Face is very well known for being, a collection of transformer models, right? The Ludwig models and Ferrari-Seek, are focusing more on sequence models, static models. And these models, these libraries, can provide a very rich set of models. But beyond that, they also can provide, libraries for additional functions, such as composing the models, text and text Forte, which were built by one of the co-organizers today, Xing, is serving that kind of purposes. And the models, the libraries sometimes can even be, very sophisticated in providing, core functions, for very end-to-end, processing of data, such as Ludwig can take, different type of sequential inputs and give you a very nice, end-to-end answer, to the analysis. So there are a lot of virtues to this type of libraries. They are very easy to build on top of existing models, and they are very convenient if your task involves only one model, okay, to use. But on the other hand, these model-centric libraries do have problems, in coming with the integration between different tasks when you use different models or models from different libraries, because they were not built with a context of solving larger tasks. The task-centric libraries, can be also very useful. They are providing implementations for typical tasks which could involve multiple highly related models. For example, you can find libraries like Spacey and Alan NLP, which can do NER, and parsing and the part of speech tagging and so forth. And they can provide you, off-the-shelf models for training, which is very, very handy and easy to use. And also, these models very often contain connotations of highly related tasks. They actually do fulfill the needs of solving not a single miniature task, but sometimes a collection of related tasks, right? For example, if after your tokenization, you can do parsing using tools from the same library and so forth. And it does provide you a kind of a pipeline feeding for complex tasks. And, they, obviously, they are valuable in the sense of giving you off-the-shelf tools for solving specific tasks. And they actually can be of very high quality, for those highly studied tasks. People have been spending a lot of time together with companies and enterprises to add functions into that. However, these type of libraries, are often highly integrated very closely with the tasks, to the point that it is overfitting the task. And if you have a different task, then it is very hard to repurpose them for those other tasks. Then comes to the solution-centric libraries, which are focusing on larger use case scenarios, such as a conversation system, which may contain a consorting of different small tasks, as I just mentioned. And these libraries are usually very rich, powerful, highly integrated, and they can allow customization of domain-specific problems. And also, they use multiple libraries, such as the one I mentioned before, to fulfill specific complex tasks. Therefore, it is very useful, when we are looking for, well-defined solutions for well-understood problems, such as chatbots and conversation systems. And also the solution-related infrastructures, including, system and machine learning interfaces are often, containers and so forth are often provided with the framework. However, these type of very powerful solution-centric libraries are only available for those most common solutions, needs and scenarios. And if you, go into a new domain, such as the clinical case report production, you probably cannot find, a very mature and easy to use libraries for that. So in a sense, you can already see that these solution-centric, task-centric, and model-centric approach to build machine learning toolboxes are really, driven by different level of integration. It is fair to say that the model-centric libraries has very little in mind about the need for integration, but only focusing on collecting, different instances of models. Then, on the other hand, the solution-centric libraries are overemphasizing integration on specific tasks. Therefore, when you need to do reintegration for different tasks or solutions, it becomes very difficult. So in here, today's talk, I would like to discuss a new approach, which is maybe taking advantage of the virtues from the libraries you saw just now, but also avoid some of the shortcomings, that we could encounter when using those libraries. We propose a simple alternative view of designing the NLP systems, which is based on a data-centric design. So why data-centric? We machine learning people, especially in NLP, applications, have no problem in all acknowledging that all we care about is to understand data well, so that we can do applications, based on that understanding. So data is the natural interface across many operations that we just discussed. For example, when we are using a model-centric library tool, to do a certain task, such as processing the data and then apply them to the model, it is the data that is connecting the processing step and the model application step. And for task-centric view applications, such as performing tokenization of the text, and then subsequently do dependency parsing, the material being communicated between the two tasks is again in the form of data. And even for larger scale applications, where you need to solve a compounded problem, such as starting from a intent classification, and then subsequently do slot filling accordingly. Again, the information being passed back and forth is still the data. So the content inside the data, in this case, can naturally connect those steps, define the dependencies between them. Therefore, it is all depending on what kind of data you are trying to transform. So there is an opportunity here to recognize the paramount importance of having a universal and generic data structure that could be treated as invariant between all these variables of tasks and applications. So this data-centric view is very convenient in bridging many different aspects of machine learning applications and study. I just mentioned about how they connect different level of tasks from different level of library building, styles, but also you can equally use them to bridge different libraries. When you use tools from a model-centric library and subsequently connect them to other tools in a task-centric or a solution-centric libraries, it is again requiring the passage of some processed data form to the receivers so that they can carry out the next step. You also often encounter different personas when developing all these different applications. For example, you may run into machine learning engineers who really work on the data model type of problems. But then you also have deployment engineers who are further away from the model, but they have to work on the data pipeline to get the thing work on deployments. And then the solution users who may be on the receiver end of the pipeline need to view and inspect the data to make sure that both the input and output are making sense and usable, right? So the data again become a bridge between all these different personas. And furthermore, for those invisible infrastructure nuances, such as parallelization, such as federation, and distributed training, and so forth, and you again can use the shared target data to bridge all these different infrastructures. So therefore, we see the data frame and data format to be an opportunity where we explore the possibility of a common denominator to establish a hinge point of standardization so that all the variety of different tasks can be unified and freely deployed and reconfigured. So let me use a use case, which is the question answering system, to explain our design rationale. Right? So as we all know, a QA system has to be built on a huge corpus of data, including reports, invoices, manuals, all sorts of structured and unstructured data. But on the other hand, you also want to build a QA system which could be reusable, for different clients. For example, the QA system could be used for a HR function inside a company, but also could be reused for other type of training, such as safety training, for example, compliance training, and so forth. And sometimes you may, if you are a provider of QA systems as a company, you may also want to reconfigure them for different use cases, right? And how to avoid doing so without every time starting from the scratch, right? And reducing the cost. So this is how a QA system looks like. It is a very long pipeline that involves many different types of tasks and model usage and data processing. It starts from query processing, like this, which really process the input query and maybe also possibly expand the query. And then you're going to use this query to start the first level of maybe passage retrieval from a big corpus to maybe coarsely find relevant passages, from some large text collection, right? And then subsequently, you may be required to do a passage re-ranking to, reorder and reevaluate the quality of those, retrieval results. And then those re-ranked ones can be, treated as input for the answer extraction, where results from all different retrieval items can be aggregated. And at the end, you are going to do answer refinement, which sometimes amounts to bias reduction, style transfers, and all that. So it is a very long pipeline involving many tools, right? And therefore, this is obviously imposing not only just the machine learning and algorithmic challenge where you need to train good models, but also it involves many deployment and infrastructure production challenges. For example, when it involves too many different tasks and using too many different diverse models and structures and tools, you have to deal with many interfaces involved in building such solution. And the interface to those engineers is often a nightmare because you need to understand the nuances not only in the form of a API configuration, but also in the exact format and nuances of the data being passed. Do they comply to adopt the same tokenization, for example? Does the bracket in different parts of the steps mean the same thing and the same scope? And all this actually could really cause a lot of a non-trivial effort, both to understand and also to reconcile. And not alone, the pipeline building issue on the algorithmic level. When you come down to deployments, you need to also deal with the supporting system that carry out training, visualization, distribution, scalability, and so forth. And that also requires a lot of interface issues. So the data-centric approach is really a good approach to help simplify the interface when building those NLP solutions, and also when building the support for those NLP solutions. And let me give you a few examples. Okay. So why it is providing the support that makes life easy. So let's first see the major challenges engineers and researchers face in building the complex NLP solutions. For example, the first problem that people often facing is the problem of very messy and incoherent data formats across all these different tasks. We all know that NLP tasks are very rich, right? At a very high level, they already divided into different microscopic tasks. For example, text analysis, involves tagging and NER and parsing, of text inputs. But then, which actually deals with a particular type of data structure, treating text, for example, as a sequence very often sometimes as a tree. And then information retrieval is another type of task. It reviews, it retrieves, the relevant documents quickly from large corpus. And in those applications, again, they deal with a lot of different data formats, which requires a lot of reconciliation between different models. Language generation is another type of task, which again requires it creates new text based on the source document, but they again have a very different data processing needs, right? And therefore they require different data structure to store them. It is not trivial to define a universal interface that is good for all these different applications. To save time, I'm not going to dive into each of these tasks to explain how they are different, but I guess you probably can appreciate that with all these tasks and the micro tasks inside it, the adoption and the usage of different data formats can be very, very diverse and rich. So it requires really, a need to, unify between different categories and the different requirements and different treatments. And beyond those larger task level application challenges, there are also a lot of tedious small issues, so to speak, of data formats, which never inspires any researcher to write a paper about. But as engineers, they have to deal it with daily, and sometimes it can be very, very frustrating. For example, the different formats of different tasks, really make life very hard, to share the pre-processing. You have to basically, pre-process the same data in multiple different ways so that they can be channeled into different task-specific modules. And different data formats from different softwares can also be very incoherent and incompatible. Therefore, it is challenging to use multiple software packages, even though we know that when we build major applications, which involves not only data processing, but also maybe language generation and the information retrieval, you have to use softwares very often from all different providers. Right? There are a lot of messiness and inconsistencies in processing the data itself, which makes the management of the data very hard. In fact, the meaning of a bracket, a semicolon, and some other tags can be very, very incoherent, inconsistent across different data sources. And also, it is often realized that many of the existing data formats are simply just not robust because there's always surprises from real data that shows incompatibility and unsuitability to existing data format. And it is very hard to fix unless the error actually occurs. Sometimes for a big pipeline, you dump in the data for training, or maybe even already start with a query. And only when the incompatibility causes a crash, you realize that there is an incompatibility, right? So this type of issues are the long list that I couldn't possibly enumerate. And that's why it is making engineers very frustrating. And in fact, in a survey that was conducted recently by Anaconda, they report that even now, more than 2/3 of the time, by engineer, for data for machine learning production are still spent on data-related issues such as data loading, data cleaning, and data visualization. So there's a need really to address this issue from the data-centric angle. If you look at all these different data structures that people use to perform all these different tasks, you may think that, well, it is really impossible to find a universal format that meets all the needs, right? Yeah, indeed, it is quite perplexing to see this, without understanding, the hidden kind of dependencies and relationship between them. But in fact, if you look at them more closely, especially with a lens from the NLP specialists, these different data structures sometimes do show a pattern. For example, there are some type of data structures which are primarily dealing with sequential data formats, okay? And such as name entity recognition and stemming, they are mostly dealing with a linear data structure, sequence structures. And then there are other tasks, such as entity resolution, event conferencing. They are more like grouping things together, to be leveraging a cluster structure. And then, of course, parsing and tagging often involves tree-like structures, right? And so these are basically how different data structures can actually fall into a smaller set of what we call maybe archetypes, prototypes. So based on this observation, we propose to define a new type of data structure, because the actual representation of NLP tasks can be very small, can be very succinct, and can be very condensed. So we basically propose to use only 3 types of archetypes, which are known as spans, groups, and links, and to represent many, if not all, of the NLP tasks. But these 3 types by themselves can be also morphed into instantiations, which specializes into more specific needs when necessary. In fact, in the paper I also copied in here, there are additional research groups who also recognize the potential to generalize NLP data formats for generic applications. So their work is actually very, very much aligned with what we presented here. So as a result, we present a system we call Forte, which is a data-centric system for text. That's Forte stands for. And this particular system adopts a morphable and extendable data representation, which compose of the following things. First of all, it consists of a ontology, which defines, just like what we see on the right-hand side, the dependencies of different, data structure at a different level of granularity. We have the template types, which are called span, link, and group. And then we have extended types, which are simply, extended from the templates. For example, in the span, you can, further extend it into tokens and the entity mentionings. And the entity mentionings can be further specialized into macro entities if you're doing, applications. But on the other hand, applications and the operations defined on these data types is inheritable from top to bottom. The one that is operating on the top can always be applied to the bottom, higher granular data types, which encourages reusability. And the instances of such a design, which can be, instantiated and designed by the practitioner, is called a DataPack. Okay, it is the actual objects that stores the actual data, and this core data structure can subsume, in our observation, almost all the commonly used data formats in NLP. And the Forte is a system developed on this very core data representation. And there are a number of important properties coming with this representation. For example, it can be built in advance or can be customized when needs happens for new applications. And these data types are managed like classes in an object-oriented programming type of development, which encourages a lot of standardization and reusability. So we see a steaming of all these diverse data types, into a DataPack, type of representation, which can, really facilitate a lot of simplification and standardization of a future system design. I'm running short on time, so I will run faster. And the second part, which is also contributing to the complexity of NLP. Okay, I will be in 1 minute. That's very difficult. Is a pipeline, and the pipeline, again, involves a lot of steps, each of which can work with the data. And again, they cause repetition, redundancy, error propagation, and all that, which again calls for the use of a standardized data format, as I just mentioned. DataPack satisfies these needs. So as a result, the life cycle of a data point in our system is going to be carried by a standardized data flow using the DataPack with all the different processors wrapped with Forte-specific interface, on this track to perform different functions. So this is very much like this metaphor where the DataPack are like the cargo of all different sorts, but the processors can work on the cargo like a container that is standardized in shape and then loaded onto the train track to carry out different applications going to different directions. There are a lot of additional functions and features of this data-centric representation. Due to the interest of time, I cannot read all of them, but the slides will be made available. They can make use of many of the tools available in our own library or third-party providers to carry out many of the functions ranging from reusable models and data augmentation. And the implementation of tasks using Forte is also very, very straightforward. You just chain together different processors, either using a program console, and we also have a graphical interface showing you how to use a graphical interface to drag and play different blocks and create a production level implementations of a task. In this case, it is about building a QA system using different building blocks. Again, I'm going to stop and move on to the final slides. All the tools I talk about is part of a big ecosystem that we are building in the company and in our research group at CMU and the MBZUI called Castle, which includes a full ecosystem of building applications using Forte, building models using Taxa, scaling models using Autodisk, tuning the models automatically using Tune, and also scheduling all the training tasks using AdaptDL on distributed environment. And some of this work are recently recognized by OSDI best papers and outstanding papers at ACL and so forth. And we're looking forward for users and developers to contribute to our ecosystem and together make it more usable for machine learning applications and developments. Okay, I'm done with my presentation. Thank you so much for your attention.
Thank you so much, Eric.
Thank you so much, Eric.
Maybe in the interest of time, if we can just get a very quick answer to one question. Just on your perspective of large monolithic sort of deep models, which are the trend, versus a library of modular components. Do you think these things are necessarily distinct, or do you think that there's, are there pros and cons of one versus the other? Or do you think that these two things are actually not a dichotomy, but can in fact, work together?
I would hope that they can work together, but the reality that it is perhaps as of now a dichotomy, because there is an asymmetric accessibility of these two territories, right? So the composable and the building block based model libraries are very accessible. Every people in company and university can work on that and contribute it. But the bigger models, due to their size and their cost in training and in experimenting, it is very hard to be accessible, for average researchers in the university or in small companies. So I'm hoping that there will be, more democratization of the bigger models and also more enthusiasms, toward the smaller models to see whether there are ways to cross-use each other. I think that the BERT model is opening a very good example because they offer APIs for people to get embeddings, representations of a text, maybe almost free. And there are many functions and ecosystems already built on that. So yeah, I'm optimistic that eventually the super monster model with powerful functions and the more agile, smaller models with more easy deployability can actually go hands in hand and make use of each other.
Thank you very much, Eric. A lot of interesting topics to discuss here. Though in the interest of time, I think we're going to move directly into our next speaker.